Today we are going to learn about understanding CNNs, architectures and their applications. We will explore various CNN architectures, their practical applications, and learn how to select and apply the right architecture for different problems.
Welcome to our video on understanding CNNs, or convolutional neural networks. In this session, we will explore the fascinating world of CNN architectures and their wide-ranging applications. CNNs are a class of deep neural networks, primarily used for image analysis and pattern recognition. Their ability to automatically detect and learn patterns has made them a cornerstone in the field of artificial intelligence. Throughout this video, we will delve into the basic structure of CNNs, examine popular architectures, and discuss how to choose the right one for your specific needs. Whether it's for image classification, object detection, or even more complex tasks, understanding the nuances of CNN architectures is crucial. Let's embark on this learning journey to not only understand CNNs better but also to apply them effectively in real-world scenarios.
Convolutional neural networks are built on a series of layers, each with a distinct function. The primary components include the convolutional layers, pooling layers, and fully connected layers. Convolutional layers are the core building blocks, responsible for detecting patterns through small squares of input data. This is where CNNs get their name, as they apply a convolution operation to the input. Pooling layers follow, reducing the spatial dimensions of the data, which helps in managing overfitting and reduces computational cost. The rectified linear unit, ReLU, is a popular activation function used to introduce nonlinearity, allowing the network to account for complex patterns. Finally, the fully connected layer maps the representation learned by previous layers into the final output, which is typically a set of scores for classification. Understanding these components and their interactions is fundamental in grasping how CNNs function to process and interpret data. The VGG architecture, developed by the Visual Geometry Group from the University of Oxford, is renowned for its pioneering depth. VGG models, particularly VGG16 and VGG19, are celebrated for their simplicity and effectiveness in image classification tasks. The architecture uses very small 3x3 convolutional filters, which stack multiple layers to increase the depth of the network. VGG16 consists of 16 weight layers, whereas VGG19 includes 19. This depth allows the network to learn more complex features, albeit with increased computational cost and memory requirements. Despite these drawbacks, VGG remains a popular choice due to its straightforward design and impressive performance on benchmark datasets. It is widely used in tasks like object recognition, where detailed feature extraction is crucial.
ResNet, short for residual networks, introduced a groundbreaking concept in CNN architectures known as residual learning. Developed by Microsoft Research, ResNet tackles the problem of vanishing gradients that often occurs in very deep networks. It achieves this by using residual blocks, which allow the network to skip layers during training, thus maintaining performance as the network depth increases. This innovation has enabled the creation of extremely deep networks, such as ResNet 50, ResNet 101, and even ResNet 152. These models have achieved state-of-the-art results in image recognition, demonstrating that deeper networks can indeed perform better, provided they are structured correctly. The architecture's ability to ease the training of deep networks has made it a staple in the field of computer vision. The Inception architecture, also known as GoogleNet, introduced a novel approach to CNN design by incorporating Inception modules. These modules allow for multiple filter sizes to be applied to the same input, capturing different aspects of the data at once. This parallel approach reduces the number of parameters and improves computational efficiency. Inception's design was driven by the need for an architecture that could perform well on the ImageNet large-scale visual recognition challenge while maintaining feasible computational demands. By using Inception modules, the network can learn to recognize intricate patterns without excessively increasing the number of computations. This architecture has been pivotal in advancing the efficiency of deep networks and remains influential in the design of new CNN models.
When comparing CNN architectures like VGG, ResNet, and Inception, several similarities and differences emerge. All architectures aim to improve the performance of neural networks in visual recognition tasks, yet they achieve this through distinct methodologies. VGG focuses on simplicity and depth, ResNet introduces residual learning to create extremely deep networks, while Inception optimizes efficiency through its multi-scale approach. These differences impact their performance across various tasks and influence the choice of architecture depending on the specific requirements of a project. For instance, ResNet might be preferred for tasks requiring very deep networks, whereas Inception could be chosen for its computational efficiency. Understanding these nuances is essential for selecting the right architecture to balance complexity and accuracy effectively. CNNs have revolutionized the field of image processing and analysis, with their applications extending far beyond simple image classification. In object detection, CNNs enable systems to not only identify objects within an image but also to locate them precisely. This capability is crucial in areas like autonomous driving, where the vehicle must recognize and react to objects in real time. Facial recognition systems utilize CNNs to analyze facial features, aiding in security and authentication processes. In the medical field, CNNs assist in diagnosing diseases by analyzing medical images with high accuracy, providing invaluable support to healthcare professionals. The versatility and power of CNNs make them indispensable in a wide range of industries, continuously pushing the boundaries of what's possible in AI technology. In designing CNN architectures, one of the critical challenges is balancing complexity and performance. Deeper networks often yield better accuracy, but this comes at the cost of increased training time and higher memory requirements. Architects must consider the computational resources available and the specific needs of the task at hand. Strategies such as pruning, quantization, and knowledge distillation can help in optimizing models without significantly compromising performance. These techniques aim to reduce model size and computation, making deep learning more accessible and efficient. Understanding these trade-offs and implementing optimization strategies is key to deploying CNNs effectively in real-world applications, ensuring that they operate within acceptable limits of performance and resource usage.
Selecting the right CNN architecture can significantly impact the success of a project. Consider a company developing a facial recognition system for security applications. By choosing ResNet, they could leverage its steps to improve accuracy, essential for distinguishing between similar faces. Another example is a healthcare startup using Inception for medical image analysis. Its efficiency allows for quick processing of large datasets, crucial in time-sensitive diagnostics. These case studies highlight how architecture selection is influenced by the specific requirements of a task, available resources, and desired outcomes. Learning from these examples provides valuable insights and guidelines for future projects, ensuring that the chosen architecture aligns with project goals and delivers optimal performance.
The future of CNN architectures is poised for exciting developments, driven by the need for more efficient and versatile models. Emerging architectures are focusing on reducing computational demands while maintaining or improving accuracy. Techniques like neural architecture search, NAS, and automated machine learning, AutoML, are set to play a significant role, enabling the automatic design of optimized architectures. As AI continues to advance, we'll see greater integration of CNNs with other technologies, such as reinforcement learning and generative adversarial networks, GANs, expanding their application scope. However, challenges remain, including the need for massive datasets and the ethical considerations of deploying AI systems. Staying abreast of these trends is crucial for researchers and practitioners aiming to leverage the full potential of CNNs in future innovations. In conclusion, understanding CNN architectures and their applications is vital for anyone involved in developing neural network models. We've explored the fundamental structures, examined popular architectures like VGG, ResNet, and Inception, and discussed how to choose the right architecture based on specific needs. The practical applications of CNNs are vast, impacting industries from healthcare to autonomous vehicles. As we move forward, balancing the complexity and performance of these models will remain a critical challenge, alongside embracing future trends that promise to reshape the landscape of AI. Thank you for joining us on this journey into the world of CNNs.